Hi folks, it's Cliff here from Down Under doing another episode on RapidTurn part 20. I've been getting a little bit uneasy about RapidTurn's accuracy on the last couple of jobs, and so I thought I would look more closely at how accurate RapidTurn is. So I will get on with that now. Cheers. Okay, well, what is the accuracy potential of RapidTurn? That's a question I'm sure many of us are wondering. I've been thinking about how I can do a more scientific test to find out just what is the potential for doing precision work. And as far as I can see, there's two main factors that affect the accuracy that I need to be concerned about. One is the repeatability of the vertical axis, calling it vertical rather than X or Z, just for simplicity. Does it come back to the same position every time when the tool rapids to the position of the finishing cut and stops? Does it stop in the same place every time? And the other factor is, what is the impact of the thermal expansion of the headstock as it warms up in this area here? Does that cause the spindle to move up and down and so affect the diameter accuracy? So this test should ascertain or give some results in that regard. So I'm just going to run a series of tests based on repeatability of the vertical axis and the temperature of the headstock. So setting it up now when it's cold, and if I rotate the spindle, you can see that diameter of the spindle nose is nice and concentric, so it doesn't matter where it stops, we're going to get repeatability. So I'll just put the camera on a tripod now and go through running these tests. Okay, well, the first test is to see what is the repeatability of rapiding down to the finish cut tool position, so it's coming down in the vertical. So let's just enter X G0 X0. Okay, that's set on 0. Raise it up. This is simulating G0 X0. That's simulating taking the finishing cut, and you can see that it's got good repeatability. G0 X0. Okay, so that's fine. Now, what is the result of thermal expansion? So we can do the same test in a few minutes after it's been running for a while. Just documenting it here. So it's about 10 AM. It's probably an ambient of about 15 degrees in the workshop, Celsius, and we've got X on 0. So let's run it at 2000 RPM now for, say, 5 minutes. Alright, we'll come back in a little while. Okay. That's noisy. Okay, 5 minutes later, it's noticeably warmer. I think I'll need to run it for another 5 minutes to see if it gets any warmer again, but let's do that test after 5 minutes. Let's do our G0X0 again now. And see, it has moved, I'm not surprised, 0.02 of a millimeter further. So in other words, the spindle has raised up 0.02 of a millimeter. That's 0.04 on diameter. Let's just check that for consistency. G0X0. And again, 0.02 of a millimeter higher. Okay, that's a worry. This is what I was beginning to suspect when I was turning my last run of parts. Okay, so let's run it again for another 5 minutes. Okay, another 5 minutes. The headstock is possibly slightly warmer. So let's say it was ambient 15, then went to 25, now let's say it's 30. Okay, let's do doesn't really matter what the temperature actually is, it's what the end result is that I'm concerned about here. So let's now do the test again, G0, X0. 3.5 now. Let's check. Just to confirm it's not due to the run out of the spindle. Got good concentricity there. Well, within 1 or 2 microns anyway. G0, X0. Yeah. So we are now 10 minutes later. We've gone from ambient 15 to headstock 25 to headstock 30 degrees, and now we have an X of 0.035. It's 7/100 of the diameter. That does fit with the sort of errors I was getting in the last run. Okay, we'll run it for another 5 minutes, see if it keeps getting worse. Alright, that's been running another 5 minutes, and yeah, it's possibly slightly warmer, so maybe gone from 15 to 25 to 30, maybe 35. Let's try it again anyway and see what the... I can hear the tone of my voice, it's sounding slightly depressed. Oh dear. G0, X0. Yeah, it's a little worse, just over 400ths, but 0.042. Just double check that. G0, X0. Yeah, exactly the same. It's got really good repeatability. That's the good news. The bad news is the thermal expansion of the headstock, because you see you've got the tool coming down from the top. I just bumped the dial indicator there. It's coming down from the top, but that's probably the worst place to have the tool from the point of view of accuracy, because you've got the bulk of the headstock material underneath the spindle, so thermal expansion rises and lowers the spindle up and down, the center line of the spindle up and down. And the other thing that's a real problem is aluminium has got twice the coefficient of thermal expansion of steel or cast iron, so you're sort of doubling the error there as well. So 4/100ths of a millimeter, that's a variation of just over 8.5 of a millimeter. That's, you know, that's over 3 thou on the diameter. Okay, you can say, well, just run it for a while to warm it up. Run it for a quarter of an hour to warm it up. So let it stabilize, and then set your finishing cut. Because it probably won't get any hotter than this. You know, even though I'm intermittently running a job and it's stopping and starting, and I put the part in and run the next part, it'll probably stabilize at a temperature, you know, maybe 35 degrees Celsius, and just run it at that. The problem with that is that you want to stop for a cup of tea or a phone call, or go and have a bite to eat for lunch and come back again, and the temperature's dropped and you've lost your accuracy. So each time you've got to remember to run it up to operating temperature. Yeah, that's not such a good thing. See, if your tool's more at the level of the center line, it's not so affected by thermal expansion. And if the headstock's not aluminium, it's not so affected by thermal expansion. So I have to be honest and say that is a couple of points against RapidTurn. As important as thermal expansion and the elevation of the headstock is, equally important is thermal contraction and the decline of the headstock. They both affect accuracy. So it's another 5 minutes has gone by now, so it will have begun to cool down. Let's just start testing it again every 5 minutes on the cooling of the headstock and the decline. Okay, we've dropped down to 3.5 there. Of course, I bumped the dial indicator, so I may have lost my calibration. I have to keep that in mind, but it's declining. It might not decline back to 0 because of bumping it. Never mind, we'll still get some useful results. Let's give it another 5 minutes now. Okay, well that's nearly another 5 minutes, and I've just been thinking of ways around this problem. One is that you could have an additional finishing tool, and that's the advantage of a gang tooling system like this. You could have an additional finishing tool that took a finishing cut on the center height of the headstock. In other words, at that level, a finishing cut, and that wouldn't be so affected by the thermal expansion of the headstock. Right, we're almost up to another 5 minutes. And another factor that's got to be taken into account is obviously the spindle is going to be warming up as well, and you'll get a small amount of thermal expansion of the steel spindle itself. So I'm keeping an eye on that, and it has increased very slightly as well as the headstock, and that is amplifying the measurement to a small extent. So we need to do a subtraction of the diameter increase to get a really accurate results, but that's not a major factor at this stage anyway. I haven't quite finished the test and let it cool back down to 0 yet, but if I even go that far. But okay, so let's bring it down to 0 now. 5 minutes sort of gone by now. G0x0. Okay, it's dropped down a little bit more, not a lot. It's about 3/100ths now. Was it 3.5 the last time? So it's taking longer to cool down, which I suppose makes sense. And the spindle will take longer to cool down as well because it's surrounded by a warm housing. But I don't think the thermal expansion of the diameter is going to be a big factor there. Alright, we'll give it another 5 or 10 minutes, but in total that was about 10 minutes cool down time, and that would equate to a cup of coffee and coming back to your job. So it's reduced about 1/100th of a millimeter, which is about 2/100ths on the diameter, so it would have reduced about 1 thou, maybe a little less because of the spindle thermal expansion. Okay, so while the RapidTurn is cooling down, I'm having a non-virtual cup of tea for a few minutes. So just having a look at the thermal expansion situation in theory. Okay, here's an online thermal expansion calculator. The headstock, so let's just enter in the values here and see whether we get a similar amount. Remember, we were raising the center line of the spindle about just over 4/100ths of a millimeter. So we want to know the length. So the height of the headstock is about 100 millimeters, but if we say 110 to allow for at least some of the base plate that it's mounted on warming up a little bit. The coefficient of linear expansion for aluminium is 0.00004012. So the initial temperature is 15 and the final temperature is 30. calculate. And what are we getting? We're getting 0.0198, but I've just realized I've entered the value for steel. So that's interesting. That's what it would be if the headstock was steel. Let's enter in the correct amount now for aluminium. 0.000023. So it's almost double, isn't it? Calculate. Yeah, and see now we're getting the change in length for that 15 degrees C is 0.038, so that's yeah, about 400ths. If we take off the diameter of the spindle nose expanding slightly, we do get it almost exactly that. So that's confirming the test. It's coming down mainly to the thermal expansion of the aluminium. Okay, back to my coffee. Just looking at the thermal expansion of metals here. So aluminium is a value of 13. That's expressed in 10 to the minus 6 per degree. But anyway, it's the number that matters. So in aluminium it's 13.1. In cast iron grey it's 5.8. So you can see there it's a lot less. Cast iron is a lot less than aluminium. So that's a real price you pay for having a lightweight rapid turn headstock that's easier to lift. I don't know, I think I'd rather have it a little bit heavier and have it more thermally stable. Okay, I've had my cup of tea, and with all the fluffing around, it's been a lot more than 10 minutes. It's feeling quite a bit cooler now, maybe not far off as cool as it was first thing this morning. Oh, it's probably a little bit warmer, but let's go G0X0. And we're getting, yeah, just under 300. So really, it's not returning back to zero in the way I would expect. That might be because I bumped the dial indicator. That sort of messed it up really, hasn't it? Oh, I don't want to spend another hour repeating the test. We definitely saw that it expanded, and for some strange reason it's not fully contracting again. I suppose I better repeat the test. Damn it, I've got an urgent job on. I'm supposed to be getting into some production machining. Yeah, okay, I better start it again. Okay, let's repeat the tests. So the temperature is probably almost cooled down to what it was, and maybe it's 20 degrees now instead of 15. So I've reset my zero. So if we go G0X0, we can see we're repeating there. Let's just do that again. G0X0. So it's nice and consistent. Repeatability is good. I've measured the diameter of the spindle nose, and it's 62.01. It's very quick, but I did it more carefully earlier. 62.01. So I'm going to run it again for a while. Okay, so I'll run it again now just to see whether we get the same thermal expansion after running it. Let's give it 10 minutes at 2000 RPM. Okay, well that was a bit more than 10 minutes. I thought I'd give it a quarter of an hour, because we know from our first test it seems to take that long to get up to operating temperature. Yeah, and maybe it still hasn't reached operating temperature. It's warmer though. Okay, let's see what it's going to be like in its X now. G0X0. Might help if I click on the MDI first. G0X0. And there we are, it's climbing again. We're nearly at 300ths after about quarter of an hour. So we'll just double check that. G0X0. Yeah, it's good repeatability. I mean, really good repeatability. So whatever backlash there is in the vertical slide, the ball screw and the inertia and all the variables, they're the same each time. So it probably doesn't matter too much about the backlash because it's a repeatable position. That's what matters. But we've got this thermal expansion problem. So I'll just measure the diameter of the spindle nose. Yeah, it's gained in diameter about 0.008. It's 8 microns. So it's gone from 62.01 to 62.018. So that's a factor of 4 microns that needs to be deducted from that error of 300ths. So we're talking about a thermal expansion of about 2.5 hundredths after a quarter of an hour, which is about a thou on the radius. So we got a diameter discrepancy of about 2 thou after about a quarter of an hour of running, and that's from not from stone cold, that's from slightly above ambient. So yeah, it's pretty well repeating the results. It would be more extreme than that if it was from stone cold. So they're the sort of errors we're talking about. Okay. Yeah, I've got a bunch of parts. I'm just in the middle of sawing off the blanks to make that have quite critical outside diameter tolerances. I need to be able to machine a diameter on the part really to within 0.5 hundredth. It would be nice if I could get it within 5 microns, and that's going to be a bit of a challenge with RapidTurn. I'm not sure if I should oh, we have an old friend turning up. I'm not sure if I should do it on RapidTurn or not. Well, this is turning into a bit of a day in the life of Cliff, isn't it? So I've been chatting to Paul for half an hour. Oh, this urgent job is going to be getting more urgent. And the headstock's cooled down, the spindle's cooled down, and I haven't bumped the dial indicator, so let's just see if it's starting to go back towards 0 again. G0X0. Yeah, see, we're already down to less than 100th, so you can see that it is returning in the way I would expect with the second test. Okay, big question, do I try and do this job on RapidTurn? Is it up to it? Well, it's always a dilemma, isn't it, when you're trying to plan ahead how to do something. If I do it on RapidTurn, it's fairly likely I'm going to have a problem with sizing. But if I don't do it on RapidTurn, I've missed a really good opportunity to find out. But the job's urgent and I can't really afford to spend time on it. So while I'm thinking about what to do, I'm putting some holes in the chuck adapter, the 5C chuck adapter, to suit this little reverse jaw chuck that I've modified to take the part. So I'm just going to put in some holes there to allow me to mount that chuck on it. Okay, that about wraps up part 20. Those theoretical tests show that there are some serious concerns about the accuracy potential of RapidTurn, and I now need to follow it up with some practical tests to find out whether or not those thermal expansion issues really are a problem in practice. Thanks for watching, guys.